Good morning, John. So I put the day and time of our final in the meeting chat right here. So the final exam is on Wednesday, 12/16. So that's a week from Wednesday. And it's from 9 to 11 a.m. is what it states on the NWAC final exam schedule, but I'll probably go a little bit in each direction, give you more time to prepare in the morning and so forth. So I'll probably give you until at least noon or 1 o'clock to take that final. So the final exam is a week from Wednesday, 12/16. I'll probably go from 9 to 1, let's say. Let me write that down, 9 to 1. The final is comprehensive. Let's go into our MyLab math course now and take a look. Now let me get that. I was doing some prep work there. So here is our MyLab math course, and I need to get to the student view. So let's take a look at homework. And let's go towards the bottom. So today we are going to be talking about section 4.5 on substitution. On Wednesday, we are going to be talking about partial derivatives. I have posted the departmental review for the final exam right here. You can start working on it at any time. It's a long assignment. It will be unavailable after the stated due date, and it's for 5% bonus. You can earn partial credit. So let me show you the assignment now. There are lots of questions, as you can see. This was compiled by the math department at NWAC for Survey of Calculus. We have a final exam review for each one of our courses. So I would encourage you to start working on this as soon as you can. You've got 9 days before the final, so you can break it down. There are 82 questions, so if you do approximately 10 per day, that would be a good way to break this all down. I am not going to write up my solutions because every one of these problems, with very, very few exceptions, you've seen several times before in the course. So there are already problem types that you've seen. Does anybody have any questions?
How many questions will be on the final?
It will be the same number of questions that are on a test in the course. So the first 7 questions will be written work questions. I can't tell you what they are because that would be violating the way we conduct final exams at NWAC in the math department.
So do we partial credit on some of the on some of the questions if we don't get the complete thing right?
So are you talking about the final exam review or the final exam itself?
No, the final exam itself. So like, let's say we didn't get the actual answer right, but we did show our work and we just kind of barely missed it.
Right. You would get partial credits. Yes, it's not right or wrong. It's partial credit. The first 7 questions are partial credit. The last 10, like usual, are not. They're answers only. Do you see what I'm saying? So just like we've been running the test for the entire semester, the first 7 questions you get partial credit on because they're written work required, and the last 10 are answers only. And I'll try to choose the questions based on that. So, and I'll try to choose those last 10. I can't promise I can do it for everyone, but for every question that is, those last 10, I try to choose where they've got multiple parts. So if you miss one part, you could still get credit on the other parts. The computer will give you credit on the other parts if you get them right. So I'm going to do that part. That part of the way the final has been constructed all along. the way the tests have been constructed all along, I'm going to do it like stay true to that. But I'm not allowed to give students the questions that are given to me from the department to put on the comprehensive final. So that's why I can't give you the written work questions, because many of those questions usually require written work. Does that make sense? Do you have any more questions? So I don't have time to grade every problem on the test for all my.
Sorry, my phone just like dropped dead on me.
Okay, that's okay. So yes, did you hear what I said, Dominic, or do you need me to repeat?
No, ma'am, I heard you. It's just, so I have my phone in my computer, and then when my phone dropped dead, for some reason, it cut me all the way out.
Does that
I did hear you.
Did make sense, what I said?
Ma'am.
Okay. I wish I could grade every problem, but I've got so many classes, and I've got 6 classes, and I have to turn around the grades so fast, and I have to look at the proctored sessions, which I have not quite gotten to your test 3s yet. I will definitely get there in the next couple of days, because I'm making sure all my classes have everything they need to prepare for the finals. So our final exam is from 9 to 11 a.m. on Wednesday, 12/16. I'm going to extend that window to 9 to 1. So you have from 9 to 1. So the final exam will appear at 9 a.m. and disappear at 1 p.m. Any questions on the final or how to prepare? The best way to prepare for that final is to do that assignment that I just showed you that had 80-some questions in it. That's a great way to prepare. Every problem on the final will come from those questions. They won't be exactly the same, though, but they'll have that same flavor. The numbers will be different. Any questions about the end of the semester? So what we want to cover today is one of those last 2 sections, and we are going to talk about, here's the final exam review schedule. Let me go over here, and what we are going to talk about is integration by substitution. So since we are going to talk about this topic, we need to review some of our anti-differentiation rules. Those will not be given to you on the final. You are allowed the survey of calculus formula sheet for the final, and that will be in question 1. But unfortunately, the anti-derivative rules are not on the survey of calculus formula sheet. So let's just review those, at least some of those. So if you're integrating, that is finding all anti-derivatives of, which we will be doing today, you want to find all anti-derivatives of, say, x to a power. How do you do that? You take that old power and add 1, but then you need to compensate by dividing by that new power. And of course, you want to add your constant of integration. So that's if the power is something other than -1. If the power is -1, like in this rule here, then what you want to do, you have the integral of x to the -1. You can move that x to the denominator and just change the sign on the exponent to a +1, so that you would then be integrating over x dx. And that is equal to the ln of the absolute value of x plus a constant. And the last antiderivative rule I want to look at today is this one. If you want to integrate e raised to a number times x, that's just e to that power, but you have to compensate by dividing by a, plus the constant of integration. So we want to consider that. And anytime you do not have the limits of integration, which we do not have here, you want to add your constant of integration. If you had limits of integration, that would represent an area. If you had the a and the b, then your integral would represent an area, and your answer would be a number. We don't have that here. We do not have limits of integration, so we need to add this constant of integration at the end. Because there are really an infinite number of antiderivatives in this case. And there's this plus any constant of integration, this plus some other constant of integration, this plus yet another constant of integration, and so forth. So let's look at integration by substitution. What we are going to do is perform a substitution to make the integral easier to deal with, and we usually call that substitution u. So u, and this is real important here, u can be a base. We're going to see that. It can be a denominator. And I should back up a little bit. U could be an entire base, an entire denominator, or an entire exponent. So you might want to jot that down, what u could be, because that's really important. So let's take a look at some problems. And at any time, if you have any questions, please stop me and say I have a question, because I want to make sure it's better to understand a few problems thoroughly than more problems and not understand them thoroughly. So let's start with problem number 1 here. So we want to integrate this right here. Well, you can see this integrand, here is, we want to integrate 9 plus x to the 8th, all raised to the 3rd power. Let me make this bigger. We want to integrate 9 plus x to the 8th, parentheses, raised to the 3rd. There's a 3 out, an exponent of 3 out, up here, times 8x to the 7th dx. And what we want to do is perform a substitution that turns that integrand into something that's easier for us to integrate. And what we do is a u substitution. So we look here, here's our integrand in here. Our integrand is everything before this dx here. So it's 9 plus x to the 8 cubed, all cubed, times 8x to the 7th. That's our integrand. And then we do have this dx, and we'll talk about that in a moment. And we want to look at that dx as well. We want to find something that will cover everything inside this integrand. Now, this du is just part of the substitution. So what we're doing here is we want to find something that covers this entire integrand here, that covers all of this. We want to be able to cover all of this. I'm sorry I went into the integral a little bit, but we want to cover all of this inside. Whatever substitution we make, we want to make sure we can cover everything inside. So what are our choices? We want to perform a u substitution. A u can be a base, a denominator, or an exponent. So look over here. 9 plus x to the 8th is a base. It's the base of the exponent 3. So this right here, 9 plus x to the 8th, is a base. So let's let u be equal to that base. U equals 9 plus x to the 8th. But what's inside here? Not the exponent, but what's inside. What's below the exponent? What's below the exponent? That's what we want to let u be equal to. 9 plus x, u equals 9 plus x to the 8th. And then we're going to take the derivative. And it's okay. This is a bit of trial and error. It's okay. Making errors is good. I've learned a lot from making errors over my math career. So I learned probably more sometimes from making errors. So it's okay to make errors. Of course, we want to minimize that, but it's okay to make them. So this is our u. Now we need to take the derivative, because what we're looking for now is how do we handle the 3 and how do we handle this 8x to the 7 dx? Got to handle all of it. We can't just have an integrand that has u's and x's in it. It has to be just in one variable. So let's take the derivative. If we take the derivative of u, we want to differentiate u with respect to x, because this integral is in terms of x's. So the derivative of this side is what we want to take. But first, let's make sure we write down the derivative of this side. So what we do to one side, we want to do to both sides. So we want to take the derivative of this side. This is du with respect to dx. So this is the variable on this side. So it's du and we want to differentiate with respect to dx. And it's very important to write down your notation correct here, because it's designed to help you. So we differentiated this side. The derivative of this right side is the derivative of a constant 9, which is 0, plus the derivative of x to the 8th. Well, the derivative of x to a power, simple power rule, it's 8 comes down, 8x to the, we reduce the power by 1 because we're taking a derivative. It's 8 minus 1, which is 7. So du dx is equal to 8x to the 7th. Now what we do is this du and this dx are differentials, and they can be split, and they work just like numbers do when you're solving. So we can move this dx to the other side. It's participating in division here. On the opposite of division is multiplication. So we can move the dx to the other side. So now we've got our setup. And for this problem, just our setup is going to help us integrate. We need to integrate here. So the first thing, let me get another color here. The first thing is we want to identify what u is. So we're trying to, what we're trying to do is convert not the integral sign, but all the rest of this that we have here beyond the integral, we're trying to convert that to u's so that we hopefully get something that's easier to integrate. So this right here, let me see if I need to click on this again, I guess, or at least the pencil. If you notice what's right here, 9 plus x to the 8th. 9 plus x to the 8th is right here. That is simply equal to u. So that's where this u came from, right here. That's u. That's u. So what have we done so far? Our u is just the base here, 9 plus x to the 8th. We still do have a 3 here. Just want to make that known. Yeah, we have a 3 here. We're just going to leave that number as a 3. We can handle that. Then what's left? 8x to the 7th dx. Well, this is what we have here. 7th dx. So all of this inside here is just our du. So this is our du now. We found du. We've got our du. And I wanted to write them in purple so you could see better. So we're now ready to convert our integral and write it only in terms of u. So we write down our integral sign. And then what's in parentheses here, that's all just u. That 9 plus x to the 8 is just u. So there's a u here. There's a u here. And then we have this 3 up here, this exponent of 3 here. We want to put that there. And then the rest of this is 8x to the 7th dx, which we have determined we can let be equal to du. That's where that du comes from. So what we have now is we've converted this into a much easier integral to work with. We now want to integrate u to a power and du. This is just like integrating x to a power. Same way. So to integrate u to a power, we're going backwards. So we want to add 1 to the power. And then we want to compensate by dividing by that power, because we're differentiating. And we will, of course, want to add our constant of integration because we have an indefinite integral. So we've gotten to here. And we look and we see this is in terms of u, but our original integral is in terms of x's. So we have to get back to x's. So we just need to know what u is. U is equal to 9 plus x to the 8th. So we can take out u and put in 9 plus x to the 8th in parentheses, because this u still has a 4 on it. So we put that 4 on 9 plus x to the 8th. Divide it by 4, copy that, plus the constant of integration. Anybody have any questions on that first example? Because we've got some tips and tricks we want to look at with some of the other problems. And so it's important to understand one here. Understand this first one, because we didn't really, it was a pretty basic integration by substitution problem. So and feel free to stop me. Let's go to problem number 10. And let's keep in mind that you only have 3 possibilities for u. It could be a base, a denominator, or an exponent. So in this case, u is a base. And every one of these problems, I have written down what u is, so that you can really see throughout the document, u is a base, u is a denominator, or u is an exponent. So I've written them by the IDs here, which is helpful for me. So let's take a look at problem number 10. And I'm skipping around for a reason. So let's take a look here. Problem number 10. And oh, by the way, I didn't do it for the last problem, but you can check all of these. And I'll try to remember to check this one. Number 10, evaluate. Be sure to check by differentiating. And if you get one of these for one of your first 7 problems on the comprehensive final, I do want you to then check by differentiating if you get a problem. If you get one of these problems. So we look at this integrand. There's really only one thing to let u be, and that's this denominator. 1 is going to be boring and it's not going to help us. So the only other option is to let u be 9 plus 6x. So I let u be equal to 9 plus 6x. Once you let u be equal to 9 plus 6x, you then need to differentiate. So the derivative of u is du dx, but I already moved the dx to the other side, which is fine. So if we differentiate this side, the derivative of 9 is 0. Plus 6, that's a number multiplier, write it down, times the derivative of x, which is 1. 6 times 1 is still 6. So I just left it as 6 dx, and this is du dx, and I move the dx to the other side. So now what do we want to do? We want to convert our integral to u's, right, in terms of u instead of x. So we have the integral. 1 has to stay because it's just a number, divided by, oh, I got a little ahead of myself. I apologize for that. Let's look at our integrand, our integral here. What do we see? We see that we can take this and replace it by u. This 9 plus 6x we can replace by u. This dx, however, what are we going to do? We've got a 6 on this side. What are we going to do? Where's that 6 going to go? Where's the 6 going to come from? So what we can do, we can sneak a 1 in here. I mean, 1 times 1 is still 1. So I'm going to sneak a 1 in there. And we're going to need a 6. But we can't just put a 6 there. We have to put the opposite, which is 1 over 6 there, which is what I did here. And this is 6 divided by 6, which is 1. And 1 times what's left is what's left. So I'm not changing the problem. We're just writing the problem in such a way that we can handle it easily. So these two multiplied together are 1. What possessed me to put in this 6 in the first place? This 6 that's in front of this dx right here, because we want to convert everything to u's. Now, we need this 6. We do not need the 1 6. The 1 6 is a number multiplier. And when we integrate, we can write down the number multiplier out front. We can write down the number multiplier and anti-differentiate the rest. So this 1 6, since it's a number multiplier, can come out in front of this integral sign. So now we're ready to convert this. And maybe I can mark this up for you. So let's get this. So once we rewrite this, and let's make sure we rewrite this. I took the 1 6 out front, and what's left on the inside is 1 divided by 9 plus 6x times the 6 dx. So let's look at this. So what do we want to look at? We now want to apply a u substitution. This in the denominator is 9 plus 6x. That's equal to u. That's this u right here. That's equal to u. And then what else do we have? 6 times dx. 6 times dx is our du. So we have du now. This du right here. We've got du right there. So we're going to convert our integral. So we're going to go down to this line, and we've got 1/6 out front. We have 1 over u. So 1 over u means we're going to divide by u. So I divide it by u. And then we have 6 dx, which is our du. That du is in the numerator. So that's all we have here. So if I rewrite this as something else, I think you can see what's happening here. So we have 1/6 we have 1/6 outside the integral. Just want to make sure everybody understands. This du is really 1 times du. So there's really a 1 up here. Divided by this u down here. And then we could put the du to the side like this. No harm in doing that, because 1 times du, when written in this form, is still just du. The reason why I want to write it in this form, because this is like integrating 1 over x. If we integrate 1 over x, that's this here, dx. It's ln of the absolute value. In this case, we're using u. In our case, we're using u. So it would be ln of the absolute value of u plus a constant. So we get 1/6 times ln of the absolute value of u plus a constant of integration here. So we don't want to leave it in terms of u, though. We want to write our answer in terms of x. And we know from here that u is equal to 9 plus 6x. So we take out the u inside the absolute value sign here and write it as 9 plus, replace it with 9 plus 6x. So our final answer is over 6, 1/6 ln the absolute value of 9 plus 6x plus our constant of integration. Anybody have any questions on this? So this problem, turned out that we needed to have u be the denominator. So we've got our 3 choices. We've got, what do we have? We've got, going back to our first sheet here, u could be a base, that is a bottom of an exponent, a denominator, or an exponent. I think I forgot an in there, but that's okay. Any questions? So let me check that one off my list. And let's take a look at 6. And in this case, u is an exponent. So I'm trying to show you, certainly today, one of each one of those cases. Problem number 6. And I promised you I was going to check one by differentiating. I don't want to forget to do that. So please call me out on that if I forget again. I just got so into the problem. In this case, we want to integrate e raised to the 2x plus 7 dx. Well, e is a number, so it's not going to make sense to let u be equal to e. There's only one other choice, 2x plus 7. That's the exponent. So let's let u be equal to 2x plus 7. Now, then what we want to do is differentiate both sides. Du dx, and I put the dx automatically on that side, is equal to 2 times the derivative of x, which is 1. 2 times 1 is 2. Plus the derivative of 7, that's an additive constant, so its derivative is 0. No contribution whatsoever. So let's take a look at this. Now, what I see is this e I ignore because it's a number, just for the purposes of what we're doing now. I temporarily ignore it, I should say. This 2x plus 7, we're going to take that out and replace it by u, but not just quite yet. And this dx, that's a variable. That x is a variable, so that dx is a variable. It means change in x, so it's varying. So that's a variable, and that dx, we don't have on one side by itself, we have a 2 in front. So we have to do something additional before we convert to u's. And what can we do? You could either do this before, or if you're careful and when you start to get better, understand what's going on, you may be able to do it in one step, but you've got to be real careful because you don't ever want u's and x's in the same integral. So let me go over here and show you what we need to do right here. And we got to get that there. Let me see. You have a question, anybody? You're more than welcome to ask a question. So what I want to do is I'm going to rewrite this in terms of x's. Keeping in mind what I need to do. First of all, I'm going to copy this e to the 2x plus 7. But we need to get it right in front of that dx. So I can put a 2 there, but we can multiply by 2, but we don't want to change the problem. So we also need to divide by 2. So that 2 over 2 is 1. And then we're going to have that dx from there. So there's no harm in putting in 2 over 2. We're still multiplying. So that's what I get. We want to get a 2 dx there, and we have a 2 dx. However, what we want to do is we want to keep this 2 next to the dx, but we want to do something with dividing by 2. That it really is 1/2. So what we want to do is we want to bring the 1/2 out in front. Like this. I'm going to bring that 1/2 out in front. And then what do we have? We have e to the 2x plus 7. We have the 2 that's upstairs, and that's all in the exponent. We have the 2 that's upstairs still there, and the dx. So that's what we have. So this number multiplier we can bring out front, no problem. You just can't bring out you can't bring out an x though. Can't bring out the variable. So what do we have now? Our u is this up here, our exponent. 2x plus 7. Our 2dx. 2dx right here. This 2dx is equal to, 2dx is equal to du. And I've covered everything. I've taken care of everything that was inside this. I've taken care of everything that was inside this integral right here. I know how I'm going to convert all of my x's. I'm not going to see x's anymore. I'm just going to see u's in my integral. And that's real important. So if we go down here, we should have this written down somewhere. We get 1/2 right there. This up here, this is e, definitely a number, want to copy it down. And this entire exponent here, this 2x plus 7 is equal to u. So we put u down for the exponent now. And then this 2dx, this 2dx right here is really du. So we can take out this 2dx and replace it by du. And that's all that that's all we get. Well, this is pretty easy to deal with. So if we want to integrate this, we write down our 1/2 out front. The integral of e to the u is easy. It's just e to the u. The integral of e to the x is e to the x. So the integral of e to the u is just e to the u. So that's e to the u. Plus our constant of integration, since we're working with an indefinite integral. We don't want our answer to be just in terms of u. We want it to be in terms of x. So we need to, this is a number, this is a number, this is our constant of integration. The only thing we have to look at is what this u is equal to. And u is equal to 2x plus 7. So we take out the u, replace it by 2x plus 7, and then we're copying down everything else. And we get 1/2 e to the 2x plus 7 plus a constant of integration. Now I promised that we would check one. So let me go ahead and do that. Let's check this. So we anti-differentiated. We need to do the opposite to check. That means to differentiate. So the first thing I'm going to do is write down this number multiplier and take the derivative of the rest. So that's 1 divided by 2. And then we move along and we want to differentiate e to a power. When we differentiate e to a power, it's e to that power times the derivative of that power. So this would be the derivative of 2x is 2. And that goes to the normal line of writing, 2. So 2 times the derivative of x is 1. So we just leave that as a 2. Plus the derivative of 7, which is 0. Plus the derivative of any additive constant, which is 0. So all we have now is this. This 2 cancels with this 2. So our integrand should just be, our original integrand should just be e to the 2x plus 7. E to the 2x plus 7. And I didn't write the dx in. I could have down here, but I don't need to because it always works like that. So you see, we got back e to the 2x plus 7. Any questions on number 6? So I do want to make a couple comments. One is, I'm not going to squeeze in another quiz before the end of the term, but I will say that every section that we've covered since test 3, you will see one question on the comprehensive final from that section. And and some of those will be written work questions. I mean, a problem like this really needs to be a written work question. Any questions on number 6? So we've done one of each type, where U is a base, a denominator, or an exponent. So it's important that you understand you could get one of any of those types. You'll have one from this section now, and it will be one that appears in this document. Of course, it'll be slightly different. So let's take a look at some other ones now. Let's take a look at number 15. And I wanted to mix them up for you so that it would seem more like what you would see on a final exam. So let's look at 15. So the difference between an indefinite integral, which is what we were just looking at, and a definite integral, which we're going to look at now, is the following. An indefinite integral, which we just looked at 3 problems, means to find all antiderivatives of. A definite integral, where you've got the limits of integration like we do here, these limits of integration from 1 to 5, that represents an area. And your answer should turn out to be a number because it represents an area. No constant of integration needed for a definite integral. So I encourage you to understand the difference there. So let's take a look at number 15. We want to evaluate, which means find the value of. This integral of x times x squared minus 1 all squared dx from 1 to 5, from x equals 1 to x equals 5. That's a pretty complicated integral. Although I suppose you could take 2 of these and multiply them together using FOIL, and then distribute the x through. That's one way to go. Probably not the preferred way to go, but it's one way to go. Let's, however, use a U substitution. So I'm going to remember a U. U is a base, a denominator, or an exponent. So here's a base. It's a base of 2. So we have a base. X, there really wouldn't be a point to letting it be x. The derivative, if we let u be equal to x, you would get u dx equals 1. So it really wouldn't get you anywhere. So let's u be equal to x squared minus 1. Then du, right here, dx is on this side. So the derivative of x squared is 2x minus the derivative of 1, or let's say plus the derivative of negative 1. That's an additive constant, so the derivative is 0. So we get du equals 2x dx. We just automatically move the dx immediately to the other side. So what do we do now? We want to take a close look at how we convert. So I copied over the integral here. I just noticed that this x appears right here next door to the dx. So I rewrote the integral, but I moved the x next door to dx. This is really x times this times dx. You can move their multiplication, and we can multiply in any order we want. So I took this, wrote it as the integral from 1 to 5 of this factor here, x squared minus 1 squared. Then I put times x at the end. That way I could see this as x dx. It would look more like this. So we have x dx here, but we don't have that 2 in front. So we want to put the 2 in front. But if we put a 2 in front, that 2 is participating in multiplication. We can't just multiply something by 2. However, if we also divide by 2, we are going to get 2 divided by 2, which is 1, and we can do it then. But that introduces this 1/2. What do we do with that 1/2? That's a number multiplier. We can bring that out in front of the integral sign. That's what we do with the 1/2. And before we go any further, we have to deal with these limits of integration. You either have to convert them to, what I would recommend is that you convert them to u's. It's easier to work that way. You could later it's more complicated because it's easier to convert them to u's. Because at some point you would have to get them back to x's. So it's easier to convert them to u's. So I put in, what I did is I made an x column and a u column. In the x column, this is x equals 1 to x equals 5. I know because we're integrating with respect to dx here. That variable there, that x, tells us that these are x equals 1, x equals 1, and x equals 5. How are u and x related? They're related via this equation here. U is equal to x squared minus 1. That's what we let it be equal to. So u is equal to x squared minus 1. So to find the corresponding u's, I can take this 5, plug it in for x here, and square it. So 5 squared is 25, minus 1 is 24. So that's where that u equals 24 comes from. And then do the same thing for x equals 1. Put 1 in here. 1 squared is 1, minus 1 is 0. So I now know what the limits of integration are going to be for our integral if we work just in u's. That's going to save us from converting back to x's at all in this problem. We'll never have to convert back to x's in this problem because we're just looking for an area, and we converted our limits of integration to u's. So now let's convert this. So this 1/2 is going out front. Our limits of integration, since I did them from top to bottom here, top to bottom, are 24 and 0. So this is u equals 24 and u equals 0. And then this inside the x squared minus 2, that x squared minus 1, rather, the x squared minus 1 is our u. And then we have a squared on it. So we get u squared. That 1/2 went out front. We took care of that. Here we have 2x dx. 2x dx is just du. So I take out 2x dx. and replace it by du. So we want to make sure everything in our integral is accounted for, including the limits of integration. So we're there. So we just have to integrate now. This is easy to integrate, but first we want to write down the 1/2 and integrate the rest. U squared, we're integrating, so we want to add 1 to the exponent. So we get u to the 3rd now. 2 plus 1 is 3. And then we want to divide by that same new exponent, which is 3. And we want to evaluate from 0 to 24. So this is 1 times u cubed is just u cubed. 2 times 3 is 6. So we get 1/6 on the outside here, or before the u cubed. And we just want to evaluate now. So first, we're going to put in the highest number first. We're going to put in the 24 for u, and we get 1/6 24 cubed minus, now we're going to plug in the 0. So we get 1/6 times 0 cubed. And if you do that calculation, you will get 2304 has the answer. Any questions on what happens if you have a definite integral, and how can you utilize a u substitution then? So that was number 15. I'm going to cross it off my list. Let's take a look at number 8. So number 8, we're going back to an indefinite integral. I found this one a bit confusing, so I want to make sure I go over it with you. And if we have time, we'll look at another definite integral. So number 8, evaluate. This is indefinite, trying to get you ready for your final where you're going to see everything mixed up. This is an indefinite integral, so we are definitely going to have put on a constant of integration. So we're integrating x to the 12th e raised to the x raised to the 13th power dx. Now, what are my choices? Remember, you can be a base, an exponent, or a denominator. Using a base of x here isn't really going to be that helpful because the derivative of x is 1. So here, we've got an e is a number, so we obviously don't want to let that be u because it's a number. We've got x to the 13th. And that is the exponent, x to the 13th. So let's let u be equal to x to the 13th. Let's differentiate. This is du, dx went on the other. I just put that over there immediately. And if we differentiate x cubed, 13 comes down. This is simple power rule. So we write down x, take 13 minus 1 and get 12. So that's our du. So what I've done is I'm looking at this. I want 13x to the 12th to be next to dx. Well, x to the 12th is in front here. So I'm going to move it. When I'm going to rewrite it and move it next door to the dx. Okay? So what I did is I just said, okay, let me make sure I'm being clear about what I want to say here. is I realized that we needed a 13. So I just put it inside the integral here. But we can't just put 13 there. We have to have 1 over 13 because we want to multiply by 1, so we're not changing anything. And I noticed that we want that. What do we want? We want that 13x to the 12 to be next door to what? Dx. We want this guy to be next door to dx. So I took this 13x to the 12th and put an arrow to make it right next door to dx over here. And this 1 over 13 is a constant multiplier, so it comes out in front. It's just a number. So where does that leave me? That leaves me with a 1 over 13 here. Now this is going at the very end, so we have this that we need to account for, e to the x raised to the 13th, e to the x raised to the 13th here. And then this 13x to the 12th, and then this dx. So I wanted to match things up with what we've got up here as much as possible. So we know what x to the 12th, what x to the 13th is. It's just our u. And we know what 13x to the 12th dx is. That's just our du. So you have to match everything up. It's like a puzzle. And we've covered everything we can. I mean, we do have a number here, but that's okay. And we do have a number here. So what do we have now? So we have 1 over 13 out in front here. This is e, that's a number, u. X to the 13th, which we have here, is just u. So we take out that x to the 13th, replace it by u, and we get e to the u. All of what's left is our du. So that's what we get. 1/13 the integral e to the u du. And now we can integrate. Fine. And so what we do is we want to write down our number multiplier and find all antiderivatives of e to the u. Well, if we want to integrate, or if we want to we can anti-differentiate e to the u, it's just going to be e to the u. And we add our constant of integration on at the very end. And so all we are wanting to do now, we don't have limits of integration to plug in. So this is an indefinite integral. So we need to add our constant of integration. And this is what we get. 1/3 e raised to the x to the 13th plus a constant of integration. Anybody have any questions on that problem? So you can multiply, you can move around factors inside the integral. And if you have a number multiplier, you can move it out front. So that was number 8. And we can check this one as well. I mean, what's going to happen here? And let's just do another one. I want to make sure you can check these. And I may have to go down here a little bit. So if I want to check this, that number multiplier can write it down and take the derivative of the rest. We anti-differentiated, so we want to differentiate to check. Now, we have this right here. We want to differentiate that. To differentiate an e to a power, it's e to that power This would be e raised to the x raised to the 13th. E to that power times the derivative of the power. So the power is this. The derivative of that power, x to the 13th, is 13. Normal line of writing times x. Reduce the power by 1. We're using simple power rule. 13 minus 1 is 12. Plus the constant of integration. The derivative of all additive constants like that is 0. So what cancels? 13 divided by 13. And then what do we have left? We have x to the 12th left, right there. X to the 12th left, check. And we have times e to the x raised to the 13th. We've got e right here. So that's correct. So you can check. Any questions on problem number 8? So let's go back and do either 16 or 14. We'll call it a day. There's 16. Take a look at that. There's 14. I don't want to do 14. Let's do 16. Evaluate. And since you have your limits of integration, we're talking about an area. So the answer is going to be a number. And I'm glad we're doing one of these because I feel like we haven't done. I think we've only done one denominator problem so far. So this is a good one. So we want to evaluate this integral from -5 to 2 dt over 6 plus t. So there are choices our choices for u are base, denominator, exponent. Well, we really don't have an exponent here. We really don't have a base in the sense of the bottom of an exponent or the bottom. Yeah. We don't have one that's the bottom of an exponent, but what we do have here is a denominator. So let's u be equal to our denominator, which is 6 plus t. So they're using t's here and not x's. We've got a problem about time here, apparently. So we have our u equals 6 plus t. So our du is the derivative of 6 is 0. That's an additive constant. Plus the derivative of t is 1. Now we're working in t, so it's dt on this side. And we want to evaluate from t equals -5. So this is t column here. T equals -5 to 2. And I wrote them in the same order. So what was low, I put low here. What was high, I put high here. So that I knew if I put them in the same way, when we get over here, then I wanted to keep that kind of consistency. So these are our old limits of integration. The new ones, what did we let u be? Because we're converting everything to u's. U is 6 plus t. So we just take our t, whatever it is, and add 6 to it. So 2 plus 6 is 8. -5 for t. -5 plus 6. -5 plus 6 is 6 minus 5, which is 1. So what are we really finding here? We are finding the integral, our new limits of integration. The old ones were 2, -5. The new ones are 8 and 1. So let's look at this here. dt times 1 is dt. dt is just du. So we're going to take out dt and replace it by du. Then we're going to look at the denominator here. It's 6 plus t. 6 plus t is exactly u. So we're going to take out the 6 plus t and replace it by u. So we have everything we need to do this problem. So our new integral, we're integrating from 1 to 8. Our entire numerator is just du. Our entire denominator is just u. Now this is really 1 over u. So this is really, this integrand is really 1 over u. And that du is on the outside, like this. So that's integrating 1 over u, which is really 1 over x. That's natural log. But in this case, it's natural log of the absolute value of u, because we're not using x, we're using u. So it's ln of the ln of the absolute value of u, evaluated from 1 to 8, or you could say 8 to 1. So first we're going to plug in the largest number, 8, and get ln of the absolute value of 8, minus this number plugged in. So we're going to plug in u. We get ln of the absolute. We're going to put 1 in. We'll get ln of the absolute value of 1. And what do we get? Well, ln of 1, if you use your calculator, is 0. Ln of absolute value of 8 is just 8. So the answer is just ln of 8 minus 0, which is ln of 8. Any questions on problem number 16? So let me come back up there. Let me get the attendance. Let me also look at the announcements one more time. Our final exam, according to NWAC's final exam schedule, is 9 to 11 a.m. a week from Wednesday, which is 12/16. Now I've extended that window from 9 to 1. So that'd be 9 a.m. to 1 p.m. So I just want to make sure that we're all on the same page with regards to that. So the final will be on Wednesday, 12/16. The window will be 9 to 1. The final will appear at 9 and disappear at 1. It is comprehensive. The first 7 questions are written work questions, but I cannot give you what those are, because I would be violating math department rules at NWAC. And the best way to prepare for the final is to do that bonus assignment that's currently available in My Lab Math. It's a final exam review. You can get partial credit. So I would encourage you all, since you've got 9 days or so, to do a few problems in that assignment every day, maybe about 10-ish problems every day. And that will break the job down for you. So I better say goodbye. And I will see you all for our last remote class this Wednesday. Take care. Bye for now. And if you have a quick question, you can stay after class and ask. I do have another conference at 10:30. Bye for now. Dominique or Sheridan, do you have a question? I'm going to go set up my other conference that starts at 10:30. I wish that we had a way to leave this one open and open up the other one, but it doesn't work like that. Bye for now.